Hello there, hope you're doing alright. Today I'm gonna start a little journey towards a black hole. But to actually know what a black hole is, we need to understand its gravity first. So let's dive in. Hello there. You see, we have known that the earth goes around the sun, but we didn't know why that was. Newton's perception of gravity was, think of a string tied to a ball. Now, if I twirl the ball around, it looks like it's orbiting my hand. And if I let go of the string, the ball just sort of flies off. This made Newton wonder, why doesn't the earth just fly off from the sun's orbit? Well, it's because according to Newton, there must be some sort of connection between them. He concluded that gravity was that connection, holding particles together. Every particle attracts every other particle with the force of gravity. But as great of a theory that was, there were still a few questions it couldn't answer. For instance, why does Mercury follow a different orbit than all the other planets? According to Newton's gravity, the Sun must always be at the center of the orbit. But that wasn't the case with Mercury. Now initially, we assumed that there must be some other astronomical body that might be between the Sun and Mercury that might have a gravitational influence on Mercury's orbit. We then looked for that object, but we didn't find anything like that. And it remained a question mark until Einstein came along with his general theory of relativity. Now, instead of imagining gravity as a force, Einstein assumed gravity to be the curvature of a 4D spacetime, an extra dimension being curved by mass. The higher and denser the mass, the more spacetime it warps. It's a little difficult to imagine in 3D, so let's take a look at it in 2D. Imagine a sheet laid across. That'll be our 2D plane of spacetime, having only length and width, but no height. Now, if we put a heavy object at the center of our plane, it gets distorted by the weight of the object. Now, if we put another lighter object around the warped space, it would fall towards the center. But if we give it a little sideways push, it starts to orbit the heavier object for a little while before it loses energy due to friction and falls towards the heavier object. Now this can also be imagined as a star-planet or planet-moon system. The only difference being, our Earth doesn't just lose energy and fall into the sun while orbiting. Relativity also gave us a logical explanation for Mercury's orbit. Along with that, it also gave us the speed of gravity, which is exactly the speed of light. Now the sun is 8 light minutes away from us. So if it were to somehow disappear, the Earth would still keep orbiting up until 8 minutes after, which is exactly how long it takes the sun's light to reach us. Now did you notice something cool? In our two-dimensional plane, they are no longer just two dimensions. The weight of the objects have curved space-time into an extra dimension. Now there is height involved. Even our little planet curves some space. So if we put another bit of mass smaller than it, then we would have a little Earth-Moon system. The heavier the object, the greater the curve. However, the size of the object isn't the only factor on how heavy it is. True weight is determined by how dense the object is. A beach ball, for instance, is huge, but as it contains mostly air, it has a very low density. Thus, it is significantly lighter than something small, say a cricket ball. So density doesn't depend on the size. Rather, it depends on how tightly the stuff inside an object is packed together. And all the mass is focused on a relatively small space. In fact, some of the heaviest objects in the universe are some of the smallest. But they are dense. Really dense. You might have noticed that throughout this video, I haven't been calling our plane just space, but space-time. Because these objects don't just warp space, they also warp time, causing something known as time dilation. Any organisms living on these planets would experience time slower than any organisms living elsewhere on the plane. Even we, right here on Earth, experience time differently than the astronauts up there in orbit. If I was up there at this moment, I would actually be aging 0.05 seconds slower than I am right now. This was one of the biggest surprises by relativity. That time isn't constant, that time is relative. So to sum up, matter warps space. The denser the matter, the heavier it is. The heavier it is, the more space it warps. And the more space it warps, the more gravity it has. Well, that's all you need to know about Einstein's relativity as the first step towards understanding a black hole. I don't really have an outro prepared, so